Hi, hello. In this second part of Chapter 5 lecture, we are going to talk about Lewis dot symbols. As you see, the title Lewis is actually named after Professor Gilbert Lewis, who is a American uh, physical chemist that were worked on early 19th century until 1940s. He worked, and he worked at the University of California, Berkeley. I just come across his Wikipedia page, and surprised to learn that he was nominated for Nobel Prize for 41 times in chemistry, but was never won the Nobel Prize. I just learned about this, and it is very hard to digest. It must have been hard for him as well to digest. Nevertheless, he's one of my favorite chemists, uh, mainly because he's so popular in this term. Whenever we discuss chapter 5, chapter 6, chapter 7, we use his name a lot, and his contributions greatly helped in understanding chemical bonding. Previously, it is very hard to understand the chemical bonding, which element is binding to which other element, why all of this, and his discovery of covalent bond and his concept of electron pairs and his Lewis dot structures that we're going to discuss uh, and Lewis dot structures and the valence bond theory, which we are going to discuss in chapter 7, are his great contributions, which actually helped us understand the chemical bonding, the nature of a bond, all of these things. So we are going to tribute to him. I wish he had won Nobel Prize, but unfortunately. Let's trivia. Well, I have so much information about him. I think 6 or 7 of his students won Nobel Prize, but not him. There's somebody really has huge grudge on him, looks like. I'm not spreading any rumors, but I wish he won the Nobel Prize. I like his work. Let's learn about the Lewis dot symbols and why he's so popular. Um, So to learn about Lewis dot symbols, first we need to know this basic definition of valence electrons. So valence electrons are the ones that are responsible to form compounds. Okay, that is when Lewis dot symbols comes. Well, you can only start working on Lewis dot symbols only when you know how many valence electrons you have and how they were arranged. And it leads back to the electronic configuration that we discussed in chapter 3, where you arrange electrons from lowest 1s orbital to highest based on how many electrons you have. So basically, valence electrons are defined as all the electrons present in the outermost shell. Okay, those are called valence electrons. So different element is going to have a different number of valence electrons, because we know that an atom, when an atom is neutral, number of protons are equal to number of electrons, and we know that each atom has its equal number of protons, which means each atom is going to have its unique number of electrons. So here, if you see in these examples, we are going to discuss on helium, carbon, and sodium. So in this example, helium, it has 2 protons and it has 2 electrons. According to electronic configuration, it fits those 2 electrons in its the lowest shell 1 and subshell S. So it fits 2 electrons there. So helium has 1s2. Helium has 2 electrons, and it put them in shell 1 is S2. So here the outermost shell is just shell 1, and how many electrons present there? 2 of them. So the valence electrons for helium are 2. And for carbon, we know that carbon has 6 electrons total because it has 6 protons. So these 6 electrons are arranged as electronic configuration, if you guys can recall, 1s2, 2s2, 2p2. So 1s2 is not useful because it is a shell 1, and 2s2 and 2p2 are the shell 2, the outermost shell. So now this is shell 1 and this is shell 2. Now what is the definition of valence electrons is? All the electrons present in outermost shell. There are 1, 2, 3, 4 electrons. It doesn't matter what subshell they were present in. but what it matters is how many electrons present in outermost shell. Let's look at another example, sodium. So sodium here has 11 protons, so if it is neutral, it should have 11 electrons. And if you count the shells, this is shell 1, this is shell 2, this is shell 3. So here the outermost shell is 3. And how many electrons that are present in outermost shell? Just 1. So sodium has only 1 valence electron. So if you can count the electron configuration for sodium, it should be 1s2, 2s2, 2p6, and 3s1. So these are your valence electrons. So this is what you need to know before we start work on Lewis dot symbols. So let's see what we are going to learn about Lewis dot symbols. So basically, the Lewis dot symbols consist of element symbols with the dots. Okay, an element, and we use the dot symbols to represent the valence electrons present for each atom. Okay, let's look at the simple example of boron. Boron has total of 5 electrons, and if you write its electronic configuration, it would look like 1s2, 2s2, 2p1. Now, the definition of valence electrons is electrons present in outermost shell. What is the outermost shell here for us is that this is our outermost shell, shell 2. So how many electrons present in the outermost shell is 3 electrons. How do we write the Lewis dot symbol for these 3 electrons is as like that. So 3 single dot electrons. So it doesn't really matter how you put them in what order. So you can put them in any different order. So just don't be so picky about how you arrange them. You know, there is some common pattern. Maybe this is our most favorite in chemistry, but it doesn't really matter. As long as you have those 3 dots, you are correct. Okay? So now let's look at the most common Lewis dot symbols for most of the common elements that we are going to use. Most of the times we are going to use Lewis dot symbols for main group elements, and transition metals we don't use so much because it gets messy because we involve d electrons there, so d shell electrons. So that's why let's focus on main group shell, where you have either S group electrons on the left side or P group, P subshell electrons on the right side. If you see one thing here, those dots follow the group number. See, group 1 here, group 1 elements here has single electrons, and the group 2 elements here has multiple electrons. Group 3, all group 3 electrons here has 3 single dots, and group 4 has 4 single dots, and group 5 has 5 dots, but 1 as a pair. This is important. When we discuss the electronic configuration in chapter 3, towards the end, if you guys remember, according to half-bow rule, we said that once you fill the lowest level subshell, then only you can fill the next one, right? So here, these 2 electrons are in the form of 2s2, a lone pair, completely filled. So there is no need to maximize bonding. That's why you start seeing the paired electrons from group 5. So group 5 has 1 lone pair and 3 single dots. What are those 3 single dots are going to represent is ability of an atom to form bonds. So for group 6, you should have total of 6 electrons in the Lewis dot symbol, which we do, but you have a 2 electron pairs and the 2 single dots. What it means is oxygen has a 2 pairs and the 2 single dots. Single dots represents the ability of an atom to make bond. In chapter 6, we are going to discuss elaborately why is that. I'm going to go over these topics again, how these lone pairs come across, why carbon has 4 single dots, why nitrogen only has 3, why oxygen has 2, why fluorine has only 1 single dot. We are going to revisit these topics in chapter 6 before I discuss about how to draw Lewis structures. So, but for now, this is the trend. Group 5 has one lone pair, group 6 has two lone pairs, and group 7 has three lone pairs, and with a single electron each. Okay, so we are going to use this information to develop how to write the ion configurations using Lewis dot symbols. And here, if you see here, group 8 has just paired electrons, no single dot. What is a group 8? Group 8s are noble gas electronic configuration. What did we discuss about noble gas electronic configurations? Are that they were inert. They were not interested in making bonds with any other element. That's why, and here you can clearly see that they don't make any bonds because they don't have any single electrons to share with anyone or to give it away to anyone. So that's why you see all lone pairs there. Now, let's discuss, let's go over some examples of Lewis dot symbols. So we just saw that boron has three electrons in its valence shell, and all three of them are used to make bonding. So that's why you have three single dots, whereas carbon has four electrons in its outer shell. So instead of using two of them as a lone pair, in order to maximize its bonding ability, carbon using its four electrons as single dots, which means carbon has the capacity to form four bonds, the maximum in a covalent molecule. Whereas nitrogen has abundant of electrons compared to carbon. So what it does is it keeps one lone pair to itself personally and three single electrons. So that's why you see one lone pair and three single dots. So those single dots again mainly represents how many number of bonds it is going to form. And you can draw these Lewis dot symbols for metals and non-metals. It's very easy to do it on main group elements. That's why we use group 1, 2, and 3 to discuss those. So sodium from group 1, so it has one valence electron, so that's what you see. And oxygen has 6 valence electrons because it is from group 6. Those 6 electrons, because oxygen has plenty of electrons, it keeps two lone pairs to itself and uses only 2 electrons for the bonding. So we just learned what are Lewis dot symbols for a neutral element, right? And what the method we used is directly identify how many electrons it's going to have and put it in the form of dots. And what we are going to learn now is when neutral elements form ions, what is its Lewis structure? What is its Lewis dot symbol is going to be? Okay, this can get a little bit tricky, so pay attention. So sodium here has one valence electron. And if you guys remember in chapter 4, we discussed a topic called isoelectronic series. And we showed, how nonmetals would like to lose electrons to achieve the noble gas configuration, and how nonmetals would like to gain electrons to achieve the noble gas configuration. So metals will form positively charged ions, which are called cations, and nonmetals form negatively charged ions by gaining electrons, which are called anions. So when these neutral elements make any changes by losing electrons or gaining electrons, so does the symbol of Lewis dot symbols, right? So ionic elements will have a different Lewis dot symbol than a neutral element. Makes sense, right? Because you have different number of electrons now. So let's look into that. A metal, sodium, has one valence electron, and naturally what it is going to do is it's going to lose that one valence electron. So when it does, its Lewis dot symbol changes from a single dot to just positive charge. And we're using charge to say that it lost an electron. So it is very easy to read. And also whenever there is charges, you need to show the charges. So let's look into, so do not forget the charge. That's why I had to included that. Let's say you have oxygen, and oxygen would like to achieve the noble gas electronic configuration in any way it can. It already has 6 electrons. To reach those noble gas electronic configuration closest to it, which is neon, it needs 2 more electrons. So it gains 2 more electrons to form a anion. So whenever you have the anions gaining extra electrons, you need to put them in a parenthesis and write those extra charges on top of it like that. So here you include a parenthesis, a bracket, and you put total of 8 electrons because it gained extra 2 electrons, converted from 2p4 to 2p6. So that's why the charge increased to -2. How do you calculate that? Number of protons versus number of electrons. In this case, you have 2 more electrons than the oxygen having 8 protons. Instead of 8 electrons, it has 10 electrons. That's why 8 minus 10 is -2. That's why you come up to this -2. So these are Lewis dot symbols for ions. If you have a metal, if it lost electrons, you don't have to show it. You don't have to show the previous, shell 2s2 2p6 because it is redundant, because it is equal to isoelectronic series of noble gas. So we don't, we kind of show that it is stable just by putting those charges instead of showing electrons. That's why it is common practice for metals to not to show any electrons if it lose electrons to achieve the noble gas configuration. But it is common practice for non-metal to show all the electrons whenever it gained extra electrons, because this is more reactive and it can donate electrons in any way. So that's why we have to show these electrons for a possibility of reaction. And this one is not in a position to give away anywhere. That's why you just need to show the charges. Or think of it as a common practice. Everybody agrees with it. All right, let's work on these problems and call it this part. Let's see. The question is asking us to write Lewis dot symbols for fluoride ion, which is F minus, potassium ion, K plus, and sulfide ion, S2 minus. All right. So I want you to pause the video and answer it before you check the answers here. So what is our plan is going to be is what we just discussed in the previous slide. First, identify their actual neutral Lewis dot symbol. Then, based on the charge, either add an electron or lose an electron. So fluorine, if you think about it, fluorine has 9 electrons, and if you write the electronic configuration of it, it should look like 1s2, 2s2, 2p5. So by saying 2s2, 2p5, we are saying fluorine has 7 valence electrons of its own as a neutral. Those 7 would look like 3 lone pairs and a single dot. So here, because fluorine comes up with a negative charge, single negative charge, which means it gained an electron. So you need to show that extra electron. So because it is an anion, you need to show all of the electrons, use a parenthesis bracket, and show that extra charge. Right. Now let's look into next one, potassium ion. Potassium has 19 electrons and it has the outer shell as 4s1 because it is from group 4. Hope I'm right. I don't know. I'm having bad feeling about it. Has to be 19, right? Hydrogen, helium, lithium. Yeah, group 4. So potassium. So 19 electrons. The last electron is present in 4s1, and it showed, +1 charge, which means it lost that single electron. Based on +1, we can predict that. So its symbol is going to be just K +1. Let's look into sulfide ions. Sulfide is from what group? Again, if you got bigger elements, you don't have to trace down to all the electrons it is present. You can use the group number to predict its valence electrons. Sulfide is from group 6 after oxygen. So group 6 electrons, group 6 elements have same number of valence electrons as its group number. So it has 6 valence electrons. So those 6 valence electrons are already arranged in the form of 2 lone pairs and 2 single electrons. Now it is saying you have -2 charge. What it means is it gained 2 more electrons. So those single dots are going to get 1 extra electron each. So sulfur with the 4 lone pairs and a bracket and -2 charge. This is how you practice writing Lewis dot symbols. Writing Lewis dot symbols is very important, not only in this chapter and in next 2 chapters, which is where we are going to focus on how to draw a chemical bond between 2 elements or multiple elements. If you're going to be successful in drawing the chemical bonding structures, a molecular structures, you need to have a really good understanding of Lewis dot symbols, or you need to get really comfortable with Lewis dot symbols. You just need to, right away should be able to tell which element is from which group and how many single electrons it has and how many lone pairs of electrons it is going to have. Then only you can be successfully write those chemical structures that we are going to practice in chapter 6 and 7. So make sure you're really comfortable in this topic before you move on to next topics.